Good morning. I'll be speaking about space age and architecture, what influenced space age design, how it impacted our lives, the development of space age materials that came out of the space program, and ultimately how we are now tasked with having to conserve these materials. The influence of the machine age on architecture and design is well documented, as seen in the streamlining of Art Deco and Modernist styles. By contrast, the space age is typically understood as more of a cliché or stylistic fad than an academic architectural influence. While there is a visual progression from the streamlined locomotives of the 1930s to the scenic cruiser coach of the 50s through to the Avanti automobile of the 1960s, that design influence did not continue into Skylab of the 1970s, although all were designed by Raymond Loewy. An interesting anecdote is that NASA did approach Loewy and gave him a stage 3 of a Saturn V rocket and basically said, make it fit. He did advise on the arrangement, size, and even color scheme of the living quarters for the astronauts to aboard the space station. Aircraft design in the late 20s and into the 30s became more aerodynamic and made use of advancing technologies to increase speed and reduce drag. Industrial designers were heavily influenced by the new streamlined aircraft design, cylindrical forms and long horizontal windows, horizontal lines and curves all conveying motion and speed were successfully scaled down for use in locomotives and automobiles, even scooters. These design elements appeared in all forms of transportation, no matter how simple. This look was also incorporated into the design and manufacture of consumer goods: toasters, fans, clocks, radios, and vacuum cleaners. The possibilities were endless. And I own that fan. Leading innovators like Buckminster Fuller gave us futuristic designs like Dymaxion car, Dymaxion house, and the geodesic dome. Post-World War II America was a period of optimism. The country was experiencing vigorous economic growth, a baby boom, and saw great advances in science and technology. With the construction of highways across America and the growing car culture of Southern California, businesses were trying to attract the attention of passing motorists. A new style of roadside architecture developed, appearing as drive-ins, diners, bowling alleys, and particularly influenced the design of signage. And in the bottom right-hand corner is Googies. And the term was coined in 1952 by architectural critic Douglas Haskell when describing architect John Lautner's Googie's coffee shop in Los Angeles. Oh, sorry, did not change that. There you go. A new design was emerging, featuring aerodynamic elements such as upswept and cantilevered roof lines, geometric, boomerang, amoebic, starburst, atoms, and parabolic shapes came to characterize this style, in addition to the use of large expanses of glass, bright colors, neon lights, and plastic paneling. Googie reflected the optimism of the time and how society was embracing technology and science and moving towards the future, but at the same time remaining accessible to the middle class. While not considered seriously as an architectural movement, Googie design represented a light-hearted and whimsical aesthetic that helped to launch the space age style that ultimately grew out of it. The beginning of the space age can be marked by the Soviet Union launching the satellite Sputnik 1 in 1957, and the subsequent decision by the US government not to be surpassed by the Soviets. The impact on popular culture was immediate and pervasive. In television and film, The Jetsons, 2001: A Space Odyssey, and Barbarella perpetuated that Googie visual style combined with space race themes. The 60s brought increasing momentum to the space race, and with it, increasingly futuristic design, employing new materials and experimenting with new shapes, masses, and volumes. And its influences could be seen throughout all aspects of American culture, in movies, TV, furniture, fashion, and music. And while Googie began as a fanciful marking concept, the futuristic design of the 60s became more purposeful, studied, and academic. World fairs have always been a showcase of innovation, technology, science, and culture, and this was exemplified in the pavilion architecture and the use of modern building materials to create new forms. The atomium in the 1958 World's Fair in Belgium, the Space Needle at the 1962 Seattle World's Fair, Tent of Tomorrow and the United States Space Park at the 1964 New York World's Fair, and Buckminster Fuller's Geodesic Dome at Expo 67 in Montreal. Attractions at Disneyland even embrace space age movement and futurism, with Tomorrowland introduced in '55 and the Monsanto House of the Future built in '57. The space age eventually inspired higher forms of architecture. Far from the kitsch of Googie, but clearly influenced by space themes, a great number of architects were highly successful in creating designs that still stand the test of time. Niemeyer's designs for the new civic buildings for Brasilia, including the National Congress and the Cathedral of Brasilia. Also his contemporary art museum in Niterói, overlooking the city of Rio de Janeiro. The same can be said about Saarinen's works. His work at the campus at MIT, Kresge Auditorium, and the chapel, with the stunning interior showcasing the Bertoia sculpture cascading above the altar, the North Christian Church, and of course the arch. A few other examples include the two towers on the upper left. 10 towers were built by the architect Gérard Granval in the Paris suburb called Créteil. These 10 towers are called les choux, or cabbages. Villot-Revel's design for 1965 Toronto City Hall features two curved towers with a saucer-shaped council chamber. And John Lautner's designs for the Chemisphere, built on what was deemed to be an unbuildable site, and the Bob Hope residence in Palm Springs, built in 1973. Appropriately, the stylistic influence of technology in flight is evident in airport design, such as the 1961 theme building at LAX and Saarinen's Washington Dulles Airport and the former TWA Flight Center at JFK. Important elements of modern material science are a product of the space race and the government's desire to make these advancements transferable to the development of commercial products and services for the public. As a result of a 1958 congressional mandate, NASA created the Technology Utilization Program. This accomplished several goals. Justification for the continued expenditure of NASA funds. It served as a tool to educate the media and the general public about benefits and dispelling the myth of wasted taxpayer dollars. And it reinforced interest in space exploration. Since the mid-'70s, the number of spin-off technology exceeds 1,800. These developments have been applied to numerous fields: transportation, communications, medicine, natural resources, energy, but also architecture. The understanding and engineering of lightweight materials and metals that have made space exploration possible also allowed these materials to be effectively appropriated into building construction materials. Some of these follow. After Apollo 1 fire, NASA developed fireproof astronaut suits, which led to improved firefighting suits on Earth. Self-righting life rafts against the downdraft of rescue helicopters are being used today. Cordless tools for moonwalks, Black & Decker developed cordless drills and the dustbuster. Then there was memory foam, water filters, smoke detectors, and the original Apollo moon boots revolutionized the design of shoes. My colleagues have the unique experience of assessing, studying, testing, researching, and conserving several significant space-age artifacts, including Space Shuttle Atlantis, Saturn V rockets, Skylab, and an A-12 spy plane, and a Corona spy satellite. Through this, they have gained knowledge on the preservation of these exotic materials that can influence the larger sphere for the use of these materials in architecture. The first case study is the A-12 spy plane, which was produced from '62 to '64 and was in operation until 1968. This was developed by Lockheed's famous Skunk Works. The A-12 was developed for the CIA to spy on the Soviet Union. The plane's design required titanium in order to resist intense heat created by supersonic flight speeds. Lockheed's supplier for titanium had only limited reserves, so the CIA conducted a worldwide search and by using third parties and dummy companies, managed to quietly purchase the base metal from one of the world's leading exporters, the Soviet Union. The Russians never realized how they actually contributed to the creation of the airplane that was being constructed to spy on their own homeland. Prior to the development of the A-12, titanium was a little used and virtually unknown material. The metal was initially refined in the early 19th century, but was not in common use due to the scarcity of the sources until the third quarter of the 20th century. Titanium is a low-density material, 60% the density of steel, and can be strengthened by alloying it to suit various purposes. It has an extremely low rate of thermal expansion and has excellent strength-to-weight properties. Although the Russians had used the metal for smaller components on aircraft, they had not developed the techniques to use the material effectively. It was not until the A-12 program that engineers were able to figure out how to effectively work the material into sheets, which then allowed them to completely sheath the aircraft. This helped pave the way to titanium later being used in bold architectural statements, such as those being created by Frank Gehry. In researching the preservation of the CIA spy plane, CSI conservators encountered the following oddities associated with the preservation of titanium. Although titanium is thought to be an indestructible material, it was found that this metal exhibits extreme sensitivity to contaminants such as chlorine, fluorine, and cadmium. For example, during fabrication, it was discovered that the chlorine-based ink of a Pentel marker used to lay out the titanium sheets caused them to fail after exposure to heat. Working with the metal was always a challenge. The biggest issue was how to roll the sheets. The Soviets never figured it out. They used blocks of metal that were milled down. Titanium is extremely hard, and trying to drill it resulted in breaking bits all the time. Cadmium-plated hand tools has an adverse effect on fasteners, which would fail after exposure to heat, and spot welds would break. For this aircraft, this particular aircraft, the biggest problem was peeling paint, related to poor adhesion between the top coat layer and what remains of the original paint. The wings had been cut off when the plane was shipped to CIA headquarters in Langley in 2007. A siliconized paint was applied after reattachment with fail. The decals were wrong, and all in all, a very poor restoration. But with a new understanding of this material, the aircraft will be appropriately specified for proper treatment. Our second case study are the two Saturn V rockets in Houston and in Huntsville. Just as NASA and DARPA encouraged the spin-off of innovations in materials, technology transfer from their weaponry and space programs for commercial uses, conservators have used a similar technology transfer from the aerospace, corrosion engineering, and coating industries to better understand the deterioration processes and the means and methods available to treat many of the iconic technological wonders of the space age. The Saturn V rockets were unknown territory for CSI. When they worked on while they had worked on aluminum sculpture and smaller types of artifacts, it wasn't until they went to Houston to bid the rocket that the task of figuring out how to conserve all of these relatively unknown materials became evident. They went through everything, one at a time. They created a bibliography of industry-wide aircraft restoration articles to understand what was being done and then culling the information. They approached experts in the field, corrosion engineers, urethane foam experts, and yes, there is a urethane foam institute, water jetting industry people. The specifications had originally called for abrasive media blasting, but through research, they found that water jetting was the accepted practice in the aerospace industry. This slide shows the range of either metal or non-metal materials in a Saturn V. The Saturn Vs are significant for the numerous and exotic array of metals and non-metal materials that were used in its construction. Aluminum, titanium, urethane foam, and even cork. The first stage was even fabricated of asbestos panels. It was important to understand what there was and how the materials were fabricated, extrusions, sheets, and so forth. Saturn V rocket was built primarily of aluminum. Interestingly, stage 1 of the rocket fired for just 168 seconds, a little over 2.5 minutes, before being jettisoned and dumped into the Atlantic. The other two components of the launch vehicle experienced similarly short service lives, and none of these stages were ever intended to be recovered. Imagine all this work to conserve something that was meant to last a few minutes. In spite of the disposability, chemical surface treatments to the aluminum and durable protective coatings that were used during manufacture had proven to be quite effective at preserving much of the historic aluminum of the two rockets. This is a photo of some of the various metals on the Saturn V, as you can see listed. All the metals were selected for the high strength, low weight characteristics, and in the case of engine metals, high heat and sulfur resistance. However, none of the aluminum alloys have corrosion resistance normally associated with aluminum. They are high copper and high zinc content. And the key to their short-term durability was the application of a Corapon, the zinc chromate primer, which you will see later. It's a green finish. The primers provided a better protection than the finish coats. These are examples of metal deterioration. And it's what you would expect when you have various metals that were only meant to last 2.5 minutes. Unlike the space shuttle, these components were disposable. The causes of deterioration included a combination of high humidity, heavy pollution, high UV, high salt aerosol off the coast, and sitting next to a farm, so they were exposed to fertilizers and herbicides. You have galvanic reactions between different metals, collection points where moisture and water collect, and UV breaks down coatings and foams. An earlier attempt to restore finishes was carried out by unknowledgeable people, and their intervention likely caused greater deterioration. Early sandblasting spread the salts and then removed the passivating layer from the aluminum. Since the rocket wasn't meant to last, NASA was not concerned with galvanic reaction, nor did they care about the paint finish. However, they were concerned with weight, and they still are. The selection of lightweight materials sometimes meant other properties were affected, such as corrosion resistance. And NASA has since learned their lesson about storing these vehicles. They must be kept in an enclosed facility, not left out to the elements. Some of the non-metal materials used include Tedlar, which is a plastic finish, Mylar, Velcro, a variety of plastics and synthetic rubbers were all developed in the early to mid-20th century, some specifically for NASA, and all were found on the Saturn V. In contrast, a simple material such as natural cork was selected for its high level of heat resistance, and it was lightweight. And it was so popular, they were concerned that they were going to actually deplete the world supply of cork. The Huntsville foam insulation system of partial foam-filled honeycomb with a nylon phenolic skin and a Tedlar seal is a version that was not used on any manned flight missions. It was replaced with a spray-on foam insulation that we have on the Houston Saturn V. This is the same foam used on the fuel tanks of the space shuttle. And my colleagues, unfamiliar with the differences heading into the Huntsville project, it was just another item that required special research and treatment development time. Early attempts to provide adequate insulation to prevent freezing of cryogenic fuels used to power the stage 2 of the Saturn V rocket had included the use of polyurethane foam-filled phenolic resin honeycomb, which was then encased in a thin film of Tedlar. The Tedlar facing mirrors a typical installation of sprayed-on closed-cell polyurethane foam in a building construction, which is then applied to a flat roof or walls prior to application of a waterproof membrane. In attempting to preserve both the Tedlar skin and the foam substrate of the Saturn V, my colleagues found that after 35 years of outdoor exposure, that the foam actually had become fully saturated with water through infiltration and condensation. Substantial and active biogrowth was found in these areas where the Tedlar was removed. And by the way, Tedlar is still used today. And a few photos showing the deteriorated finishes on the stage 2. The spray urethane foam insulating the Houston tank on the left was extensively cracked, damaged, blistered, trapping water and concealing corrosion of the aluminum tank. While what seemed to be a better preserved version in Huntsville, with the Tedlar appearing to be intact, actually turned out to be far more complicated. Trapped moisture within the honeycomb cell and foam structure and large losses and damage to the Tedlar were uncovered after paint removal. The Tedlar remained in relatively good condition and most was saved with some repaired areas. And as I said, Tedlar is still used today. But what is interesting is that closed cell foam isn't perfectly closed cell. It does have a permeating, and under solar gain, there are pressures that form moistures into the cell, and urethane does not bond well to a wet surface. And this is just some spec information on Tedlar and cross sections of the foam. Another material is Mylar. The rockets use different colors, and each one had its own properties for reflectivity. So in this particular case, the Mylar is acting as a reflecting insulator to keep cryogenic fuels from overheating. Of the Saturn V's, Mylar survived in only a few instances. It isn't UV stable, and it deteriorated. And Mylar is another one of these products that had a spin-off application. As you can see on the right, it's used as a wall covering. And this is just a quick slide to show the previous attempt to restore the rocket in '84. Research into previous treatments show that these were misguided attempts at repairing the problems without first understanding the causes of deterioration, and this caused more problems down the road. But we learned from those mistakes, and more importantly, utilizing the most current techniques by borrowing from corrosion and coating industries. The main problem stemmed from overly aggressive coating and corrosion techniques that were not effective in dealing with the main problem being soluble salts. Previous sandblasting spread salts over the surface, then sealed them with a new coating system. Catastrophic failure of the coating was visible in a few short years. CSI tested the appropriateness of ultra-high high-pressure water jetting on aluminum test coupons and original tunnel covers from both Saturn V's as a method for removing coatings, corrosion, and surface contaminants such as soluble salts. Automotive and aerospace companies have cleaned manufacturing components and removed thermal coatings with UHP water for many years. And as you can see in the photograph, the water jetting technique could be tailored to take it down to bare metal or just to remove the top coats, leaving the original Corapon primer and fabrication stamps below intact. And just a photo of the technique. Once the proper testing and analysis was complete, the work moved to full-scale treatment, and it was decided that it was more important to remove soluble salts from corrosion pits, so it was cleaned to bare metal. And unlike NASA, City of Houston has very strict VOC regulations, which prompted CSI to use a waterborne coating system. In addition, the client wanted a coating system that could be touched up with minimal preparation and touch-ups that would visually integrate with the existing finish. And the final product. This is the Space and Rocket Center in Huntsville, but both Saturn V rockets were treated the same way. And the decals are actually recreated by a company that produces bus wraps. So we have provided a few examples of space-age materials and how we have attempted to solve problems, but there are other materials that have been used in architecture and we will need to learn how to deal with. The following are but a cursory look at other technologies developed by NASA for spaceflight and landings that have been applied to consumer and commercial building products and processes. Nastran, a finite element analysis program, was developed by NASA and is used today throughout the world in aerospace, automotive, and maritime industries. Software was also developed for architecture, permitting these exotic designs such as Frank Gehry and others. But initially, Nastran was used by PPG to develop new technology to create glass walls. NASA created all kinds of protective coatings. Statue of Liberty restoration, a zinc silicate primer based on a 1970 NASA patent was specifically developed to provide superior corrosion protection for the iron armature. Fiberglass and Teflon tension fabric roofs are an outgrowth of a material formulated by NASA from 1967 for new spacesuit fabric. And a recent development that I found is an open lattice composite design, allowing for lightweight, stronger structures that don't corrode or rot. The strength comes from the efficient geometry, isosceles triangles that form a truss of pyramids, which what gives the truss its unique strength and stiffness. The space age represents monumental technology and human achievements whose influence ultimately extended far beyond the space program itself. In many ways, technical innovations and materials that are synonymous with this period for exploration were disseminated to the public through a variety of consumer goods, building technologies, and processes. From new alloys born out of improved mining, refining, and alloying processes to synthetic materials engineers and labs, American design directly benefited from the increased variety and range of properties afforded by these new materials. The architectural expression and innovative construction that resulted is increasingly becoming the charge of preservationists and conservators, and we need to work with industries outside of conservation to find solutions to preserve the space age. Thank you.